In the last video, we talked about different mobile phases and how I can change and play around with mixtures or pure samples in order to help improve the separation that's going to take place on the plate. And we ended up with something like this, and I was like, listen, everybody, it's going to take little bitty baby steps, just little bitty tiny things that you want to do in order to make the separation a little bit better. So when you go in, and if you are in research and development, you want to do very small, little bitty steps, one at a time, until you get a better separation to take place on your plate. Do not change these percentages by quite a bit, because you're going to see a drastic difference here in this one example, just in a 5% difference between the mobile phase compositions. So this is where we ended, and we need to now pick up off of this idea about solvent strengths and more a little bit about the mobile phases that can take place in a lab environment. So I told you that, whoa, this is going to be a holy trinity, the holy trinity of mobile phases. So what do I mean by the holy trinity? Okay, well, this is what we're talking about. So if you are expected to do research and development, and again, for the most of us, we're going to go into a lab, everyone, and we're going to have a SOP that we're going to follow. And that SOP will tell us what we should be running plate-wise, what we should be running for our developing solvent, and so forth. So we do not have to play a guessing game here. But if I was kind of assigned a task, and my task is to try to do something new and fresh and innovative with HPTLC, or try to make certain things a little bit better than what we've done before, there are going to be some things that I can keep in mind with mobile phase selection. So the Holy Trinity basically means that on one side of the triangle, so three, is a proton acceptor, and a proton acceptor is basically, in other words, a base. Next, on the other corner of the triangle, we get a proton donor, and a proton donor is basically an acid. And then on the other corner, I get a dipole interaction. And the dipole interaction is the idea that the solvents are going to interact with each other. Of course they will, through the process of dipole. So with those three kind of concepts in place, hey, I can play around with some bases, I can play around with some acid, I can play around with some polarity of just various solvents. Then we get a categorization that can take place within those three parameters. And they will label them group 1, 2, 3, 4, 5, 6, 7, and 8. So that's what you're seeing here in the middle of the triangle. Now, if I go back and I take a look at the polarity index here, hexane on this screen, of course, is straight up nonpolar, everyone, right? There's all carbons, all hydrogens, no free pairs of electrons, no functional groups. It is just simply 6 carbons in a row with enough hydrogens to make them all happy. And that polarity index look is very close to 0. So there's no polarity at all. This is a non-polar type of situation that we have. And notice it says selectivity group here. It just completely dashes that out. It's just like, nope, we're not going to identify it. This is just strictly non-polar. After that, the isopropyl ether comes next, and that polarity index increases a little bit, and that will be in group number 1. And diethyl ether is also in group number 1. So if I go to this Holy Trinity triangle and I take a look at the Father, Son, and Holy Ghost, I'm going to see group number 1 is over on this side. So it's going to be further to the right-hand side, which is further to this kind of concept of dipole interactions. It is polarity driven, no really hardly any acids, no really bases. But at the same time, it's given me an idea of what I could use on my end in order to get these things to at least somewhat move and to at least somewhat separate. So this is just a classification scheme. That's all that it is. And I'm not going to go into any more detail than that. So again, this is not an organic chemistry class. This is an instrumentation course. And I just need you to understand that there is somewhat a kind of logistics behind what could be complete chaos and madness when it concerns how do we select the appropriate mobile phase for the analysis that we want to attempt. All right. Here are just different examples, A, B, C, and D, each ran on a different plate. And what's happening here is that we are just playing around with different mobile phases to see how these components separate it from each other. So notice in number 1, it really doesn't separate the green and the yellow quite well. In B lane, it does kind of separate a little green from the yellow a little bit more. It does a better job. Sure it does. And then in B, it looks like this purple band actually moves up from its starting point a little bit further than what lane A did for us. Lane C, it looks like the yellow now has bypassed the green. The pink is still there. The blue and the orange are really close together. I've got to be careful. There's a very slight color that's right here. You probably can't see it that well on your computer screen, but it's there. And then I get a purple one that kind of moves up from the point of origin. Absolutely it does. But the whole idea here is to try to figure out a way that we can separate these and feel really good about what we did. And then in B, it looks like the purple went up, and then this bluish band shows up a little bit better. This orange one is there, the blue one's there, the pink one's there, the green one's there. And then some people might say, well, what about the green one? Well, again, this is the whole concept of mobile phase selection. So all 4 of these were analyzed with different mobile phases, and you're seeing that these mobile phases are playing a very drastic kind of role in determining how these things begin to separate and the order in which they will separate. Notice that in D, we also get very hazy, fuzzy areas, and quite often we do not like those when those show up. We prefer bands that are very, very tiny, very slim, no haziness, pretty much just a straight line all the way across like you would have when you mark it with a pen. So this is kind of the idea of mobile phases and how intricate this whole area might be, because again, it is drastic changes with just a little bit of a difference between what is present. And there is a little bit of organization that can take place. Of course there is, and this is what we call the Holy Trinity. So we're looking at bases, we're looking at acids, we're looking at dipole interactions, and depending on how that scheme needs to be laid out, then this will give us an idea of the type of solvents that we need to pick in order to kind of go that route. So for instance, if I had a compound and that compound was, let's say, acidic in nature, then here is my acid group, and that means I probably want to be kind of closer on this realm of the Holy Trinity triangle. So I probably need to be looking for something like solvent set number 7 or solvent set number 8. And solvent set number 7 and solvent set number 8 will kind of start here and go all the way down. So it looks like I probably need to use something like this on that realm, and that way I can get some separation and some interaction between those components that we need to separate. Of course, that's kind of what we do. All right. Next up, we talked about stationary phase. We've talked about mobile phase now in a little bit of detail, and now what we're going to do is focus on the gas phase. So we said the gas phase is very unique to the field of TLC, and of course to HPTLC as well. When we talk about one, we talk about the other one now. And the gas phase is going to be caused by the evaporation of the developing solvent. That's where this is coming from. So that is why I told you that you are making the developing solvent, you are not making the mobile phase. So when you pour your developing solvent in, a part of that could volatilize, a part of that will go up into the upper realms of the chamber, and that creates the gas phase that's inside of the tank. When that gas phase is created, that has now changed the composition of your developing solvent, and that leaves the mobile phase, prim and proper, that stays behind. All right, so this gas phase is really what fills the chamber. That is what this is going to be all about. So lids on chambers are very important, folks. You've got to put lids on them. And I will say that many things can be used as lids. So for instance, glass pieces can be placed on top of these chambers, and that will help prevent the loss of vapor. We can even use aluminum foil. Aluminum foil can also be used because if it is on there tight enough and if it's on there securely, it's going to be okay. It's going to keep those vapors on the inside and nothing's really going to damage. the aluminum, but never, 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 never use parafilm. And the reason is because parafilm loves to react with organics. And if I use some organics that's in my developing solvent or my mobile phases, then up it goes. And when it goes into the upper realms of the chamber, guess what it's going to do? Yum, 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 yum. It's going to eat all the parafilm. And then before I know it, there's going to be holes in the parafilm. And if there's holes in the parafilm, then guess what? My gas phase is not trapped because my gas phase is now leaving and it's going into the room that I'm working in. So never, ever, 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 ever decide to stretch parafilm over the top of these tanks as you manually develop them or as you automatically develop them through instrumentation. So glass is going to be fine. Aluminum is okay. It's out there. It can be a thing as well, but never plastic or never parafilm. It will interact with that parafilm, and now we are in a pickle because we're going to have to start all over in order to get the proper types of separation that's going to take place. All right. Now, as I say, the gas phase, we allow time for the gas phase to develop. So there's a couple of terms here that we want to talk about, and the first one is going to be called saturation. So if I'm using some plates and I'm in TLC theory and I've got samples that will go onto the plates and these things are going to separate, blah, 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 blah. Well, there's a whole kind of thing that I've got to do in the beginning before I go through the chromatography aspect of what we're getting ready to do. So saturation is one step in this process. So saturation is basically this concept that the solvent components are evaporating. So this is an idea that gas phase is actually getting generated through this step. Most of the time, this is going to require a saturation pad, and those saturation pads are very important because that's going to help us create the gas phase and to kind of help us fill this chamber before we place our plate on the inside for the development. And then we often give this about a 20-minute run, or at least a wait period. So what goes on is that I am being tasked to do TLC, and I know that I've not really explained TLC or the process of how to apply sample. We'll get to that. It's just the idea of the process as of right now. So when I get the tank, I'm going to have the tank right here. There it goes. And then what I'm going to do in the very beginning, I'm going to pour my developing solvent into the bottom. So when I pour the developing solvent on, I'm then going to place a lid on the tank so that way that gas, once it gets created, is not going to escape from me. And then I'll wait. And when I wait, I'm going to wait about 20 minutes. And what's going to happen is that that gas phase, if there's components in that developing solvent that will be volatile and will evaporate, that gas phase is going to be created. And I get this third interaction that's going to be happening. So we talked about stationary phase, we talked about gas phase, and now we're talking about the gas phase and the mobile phase. So all of these are interacting together and creating and helping me in my separation in the plate. All right, so as I wait for 20 minutes, what's happening is that I've also got a piece of filter paper on the inside or some type of saturation pad on the inside of this tank. So what that means is that I get a brown, in my brown square here, this is going to be a saturation pad. I want you to think of it as like a piece of filter paper. It's very thick, it's very absorbent, it's going to suck up these developing solvents that we're going to be using throughout the analysis, and it is there just to help create the gas phase and to let it create it a little bit faster and a little bit more efficiently. So that is the purpose of the saturation pad. So the saturation step that we are talking about is just this. It is developing solvent in the bottom, it's my saturation pad in the tank, and it is my lid, and nothing else is going on. So this is the step of saturation. 20 minutes is typically the go-to time, especially on HPTLC instrumentation. So I allow it to do its job. Nothing's going to happen. I'm going to wait for 20 minutes, and then I'm going to come back to the tank, and that's when we're kind of picking up after that. All right. Another type of definition that we can use or that we can talk about here is something called a preconditioning step. So preconditioning is a little bit different, and a lot of people get these confused. They think that saturation is preconditioning, but it is not. So what's happening in preconditioning is that the gas phase, once that gas phase is generated, it is then adsorbed onto the stationary phase, which is basically my plate. But nothing else is coming in contact with it. So the mobile phase at this point is not coming in contact with the plate at all. So how does this happen? Okay, well, let's say that we've got a tank, and here's the tank down here below, and I put a plate on the inside of the tank. If I lower that plate all the way on the inside and let it rest on the bottom of that tank, then of course what's going to happen here is that the mobile phase is going to come in contact with it, and the mobile phase is going to go up and 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 up. So of course I don't want that to happen. The only thing that I want is the plate to come in contact with the created gas phase that we have done from the first 20 minutes. So what happens here is that we allow the plate to dangle. So if I was using maybe some instrumentation, it will lower the plate in, but it will not allow the plate to come in contact with the developing solvent that is down here in the very bottom. Instead, the plate is just hanging out. The plate is there with the gas phase. And just because of that, no separation is taking place. Nothing's moving anything through the stationary phase. No travel is going to happen. The only thing that we're doing is we're allowing the gas phase to kind of latch on to the upper parts of the plates for sure, and just to create something that's a little bit more uniform, that already has the gas phase ready to go, and maybe, just maybe, this will help my separation a little bit better. As you can imagine, as my components travel up the plate, a certain thing's going to go on. And if the plate is lowered and if the plate begins to automatically develop, it's going to take some time for the gas phase to kind of latch on to that plate. So as my components are traveling up the plate, it is seeing that stationary phase, but it is seeing that stationary phase that has the gas phase on it already. So by the time it goes in the beginning, it's not going to see too much of that gas phase because this stuff is going to take off like a rocket. But as the development begins to happen, it takes a little bit longer and longer and longer for it to reach the upper parts of the plate. So at that point, absolutely, that plate is going to have some gas phase on it already, and the composition of that area of the plate is going to be a little bit different than the bottom pieces of the plate. So hence, preconditioning might be a thing that you want to do. So if I am doing it by hand, though, there is a thing that we've got to do, and that thing is to be very creative with the types of troughs that we have in our tanks. And I'll talk about that in just a minute. All right, so this is the idea of preconditioning. Again, we're going to expose the plate to the gas phase only. It is not going to come in contact with the mobile phase at all. And all this is it's preconditioning the stationary phase, which for the most part is just going to be the silica. So that way, that particular evaporative component can be on the surface of the plate, and it can be there, and it can be ready for your samples as they travel up and up and up. All right. Another term that we're going to be using here is called evaporation. And evaporation, of course, is the evaporation of the developing solvent. That's what this is. So the developing solvent is, again, the most appropriate term that you will use for what you make. And there is a component of that that will be very volatile. Those volatile components will evaporate. They will fill the upper realms of the tank, and they're going to sit up there and they're going to hang out. And then they will start attaching themselves to the plate once that gets lowered. So the evaporation is very important, But at the same time, I want you to understand that the plates, when they are lowered, this gas phase does come in contact with the surface of that plate, absolutely. And that gas phase can leach on the top of that silica, and it can stay there for a little bit. But you know, these things are volatile, which also means that once they go on to the surface of the plate, then guess what? They can and all over again. So that evaporation step is also taking place. So I see a different type of evaporation in that area of the plate as things begin to kind of travel and things begin to move. In addition to that, as my plate begins to suck up the proper mobile phase, it's going to suck up and up and up and up and up. And then what's going to happen is down here, where it's really wet, really saturated, if there are volatile components, then guess what? So it's evaporating from the actual mobile phase as well as it begins to travel up. So evaporation is everywhere. It is taking part in 3 different areas. My developing solvent is evaporating, and then the upper part of the plate is also experiencing evaporation because the gas phase is latching and the gas phase is volatilizing off again. And then the other thing that's going on is the lower plate, which is where the mobile phase actually is. That's also evaporating over a course of time as this system begins to develop. So evaporation is a very key role. And if you have things that are very volatile, then you're going to experience evaporation playing a more important role than something that's like water and some type of heavy acid as your developing solvent. So again, it's all about the mobile phases. It's all about what you're choosing and what is present, and that will give you a better idea of what maybe is going to be in play when we begin our separation. Finally, another thing that we want to talk about here is something called a secondary front. And a secondary front is coming from a solvent, and that solvent is going to be a mix of different things. So what happens in a secondary front is that during the development, as you're waiting for that plate to kind of do its job and to separate these components of your sample, then the mobile phase can actually separate. And when the mobile phase separates, what's going to happen is that a front is going to form. So here is my plate, and let's say that I've developed it and it's ready to go. And I've taken the plate out. Wherever my mobile phase has reached, I'm going to take a line and I'm going to draw right across from it. So that is what we would call the mobile phase front. So with that said, that's where I'm going to base my RF values. So when I calculate my retention factors, my RF values are going to go from the point of origin all the way up to the top, and that is how I'm going to calculate my RF. Again, that's going to come later in the lecture series when we get to that point. Okay, well, there is a funny thing that can happen here. When I develop these plates in this particular type of TLC or HPTLC type of situation, there is a chance that as my mobile phase is getting sucked up, one component of my mobile phase is going to start separating and running a little bit faster than the second one. So if you develop a plate and in the imaging you see a secondary line, so primary is the highest, and this is where really the mobile phase went. But if I see a secondary line, then that means there was a component of my mobile phase that traveled way slower than another component in the mobile phase. So that one took off. That one was like a flying rabbit that just went pew all the way up the plate. And then my secondary front here that has formed, and hence the 2 with the little circle, a secondary front, has formed because that one is taking its measly little time. It is in no hurry. It is on a Sunday drive, and it is going up the plate without an issue. So that is what a secondary front is all about. All right, so in the next video, we're going to pick up from here. We're going to keep talking about these gas phases and keep talking about maybe some different types of situations that I'm going to see in this whole kind of review of these discussions.